Hello everyone, welcome to tutorial number 7. Okay, so it's under rotational work and energy. Okay, so I'll just be pausing for the questions here. You read the question and then start explaining, yeah, after some time. Okay, so here we have question 1. Okay, so question 1 here, we want to find how long it takes for this rim to accelerate from rest to an angular speed of 210 revolutions per minute. Okay, and we also find the number of revolutions it makes during this time. Okay, so angular acceleration, we know it's given as alpha equals final angular speed minus initial angular speed over the time. Okay, simply the change in the speed over the given time interval. Okay, so the initial angular speed here, we know it's 0. Okay, so our formula here, we have angular acceleration equals final minus initial over time, and we know that our initial angular speed is 0. Okay, so you know the final angular speed. If we convert that 200 revs per minute, we are having 210 over 60 seconds, giving us 3.5 revolutions per second. Okay, so if we convert this further to radians per second, we are going to use this method. 1 revolution per second is going to give us 2 pi radians per second. Okay, since we have 3.5 revolutions per second there, we simply cross multiply and it's going to give us 22 radians per second. Okay, so we go back to our formula here. We know that angular speed equals, the initial was 0, so we remain with the final over the time. Okay, giving us 22 radians per second over t. So we don't know what t is. It's the one we're looking for, so we're going to pause here and we remain with equation 1 for now. So we have that alpha equals 22 radians per second over t. Okay, so notice also that for this rim to rotate, there is a torque acting on it. Okay, so the torque is given as the moment of inertia times the angular acceleration. So torque here is simply analogous to Newton's second law, where we have the mass equals, the force equals the mass times the acceleration. Okay, so in this case we have the torque equals moment of inertia times angular acceleration. Okay, so from here we can also note that we can find angular acceleration. Okay, we'll have angular acceleration being equal to the torque over moment of inertia. Okay, so this can be our second equation for the angular acceleration. So another thing also to note, the torque here is given as tangential force times the radius. Okay, it's given as the tangential force times the radius. Also, the moment of inertia for a disk, we know it's given as half mr squared. Okay, that's the moment of inertia for a disk. So if we want to use equation 2, okay, to find angular acceleration, we can work this further and we have angular acceleration equals force times the radius, which is the torque, over the moment of inertia for a disk. Okay, that is mr squared over 2. Okay, so we're going to have 2F over mr, and we know what the force is. We're given in the question. We know what the mass is and we know what the radius is. So these are the values. You simply replace or substitute, and we're going to find the angular acceleration using equation 2 as 0.264 radians per square second. Okay, so since we have found the angular acceleration using equation 2, we can put this value of the acceleration into equation 1 and simply solve for t. Okay, so we put back this value into equation 1 and solve for t. So as we can see here, now find t using equation 1. We know that equation 1 gives alpha equals omega final over t. Okay, so we make t the subject. We have t equals omega final over alpha, and omega final, we said it's 22 radians per second after converting. So we'll have 22 radians per second over 0.264 radians per square second, giving us 83.3 seconds. Okay, so this is the time that it takes for this rim to accelerate from rest to 210 revolutions per minute. Okay, so now that we have found the time, we can now find the displacement, or rather the number of revolutions it makes during this time. Okay, so the average velocity here gives us displacement over time, where the displacement here is going to be our number of revolutions. Okay, and we should also notice that the average velocity is given as the final plus initial divided by 2. Okay, since our initial was 0 here, we're simply going to remain with the final divided by 2. So from this equation, we can make the displacement, or rather theta, as the subject. Then we'll have theta equals average velocity times the time. Okay, but here we want to find the number of revolutions, so meaning our final speed, or rather our average speed here, has to be in revolutions per second. Okay, so if we do that, like we have seen here when we're beginning, we had 3.5 revolutions per second as our final speed. So it's the one that we're having even here. We're going to have 3.5 over 2 revolutions per second multiplied by our time, giving theta, or rather giving us 146 revolutions. Okay, so this figure here, 146, you might get 1.5 point something, which is okay. I've simply rounded off. Okay, so now we have found the time that it takes to accelerate from rest to 210 revolutions per minute, and we have also found that it makes 146 revolutions during this time. Okay, so that was question 1. So we move on. Question 2. You can read. Okay, so here we have a cylinder with a cord wound on it. Okay, so this cord is attached to 100 grams mass. So the mass therefore is released, and then it falls, or rather drops 180 centimeters in 1.5 seconds. Okay, so now we want to find the moment of inertia of this cylinder and the tension in the cord while the mass is falling. So you can look at this cylinder from one end. Okay, from one end, or let me say from the side. So if you look at this cylinder together with the cord and the mass from one end, it's going to look like this. So we have this chord, which is a wound on the cylinder, and it's attached to a mass. Okay, so this mass is going to fall a distance, or rather a displacement of 180 centimeters. Okay, so notice here that while this mass is falling, it's causing this cylinder to rotate. Okay, it's causing this cylinder to rotate, and because the mass is attached to the cylinder by a cord, there's going to be some tension in that cord. Okay, so the force that is making this cylinder to rotate here, we consider as the torque. Okay, so if we sketch it, we're going to come up with something of this nature. Okay, this is what we are having. So we can see that the tension there is acting upwards, and the mass, or rather the weight of this mass, is acting downwards. Okay, so the tension going upwards, the weight going downwards, these two are causing a downward acceleration. Okay, so as you can see, we have tension upwards minus the weight, which is acting downwards, are going to cause a downward acceleration, which is negative. So we make the tension the subject here. We're going to remain with tension equals mg minus ma. Okay, because the mass is accelerating downwards, so we expect the acceleration to be negative in this case. So we factor out the mass. We have tension equals m multiplied by g minus a. So this is our equation 1. Okay, so since we want to find the moment of inertia here, let us consider the torque now. Okay, we consider the circular force. So we are going to have that torque equals tangential force multiplied by the radius. Okay, so our tangential force in this case is simply the tension. Therefore, the torque is going to be tension times the radius. Okay, but we also know that this torque is equal to moment of inertia times the angular acceleration. Okay, so we are going to equate TR equals I times alpha. Okay, also notice that alpha is given as A over R, which is the acceleration over the radius. Therefore, we have TR as our torque. Okay, TR as our torque equals moment of inertia times our alpha. Okay, so we can make T the subject from this, and we'll have tension equals IA over R squared. Okay, so this can be our equation 2. So now you look at this equation 2, it's an expression for the tension. We can simply substitute this into our equation 1. Okay, we substitute this into our equation 1, then we remain with one unknown, which is the acceleration. So let's do that. We substitute equation 2 into 1. We are going to have IA over R squared equals mg minus a. Okay, it's going to be m multiplied by g minus a. Okay, so from this we can find our moment of inertia as I equals mr squared multiplied by g over a minus 1. Okay, so I'm skipping some steps here, but I believe you're going to work this out on your own. So we're simply making I the subject, and we're coming up with equation 3 right here. So notice that in this equation we have one unknown, which is the acceleration. So now the only thing remaining for us to find the moment of inertia is to first find the acceleration, okay, of this mass, or rather the downward acceleration. Okay, so since we know the height, through which it's falling, which is 1.8 meters. We also know that it's starting from rest. We also know the time it takes. So we can find the acceleration from this equation of motion here. We have h equals initial speed times t plus half at squared. Okay, but we know that u is 0. Okay, so if we work this out, we're going to find our acceleration as 1.6 meters per second. Okay, I hope you're following. So you work, or rather you find the acceleration using this guy here. Okay, so if you find if you work out or solve for a, you're going to find a as 1.6 meters per square second, and from there you substitute the value of a, and you also substitute all the other values which are given in the question, and then you're going to find the moment of inertia. We have I equals, our mass is 0.1 kg, which is 0.1 times the radius squared multiplied by g over a minus 1. Okay, so from which we're going to find our moment of inertia as 0.0295 kg square meters. Okay, like that. All right, so in case you're behind, I'm a bit fast here. You can always post your questions on Telegram or even on WhatsApp. Okay, so now things have become more simpler. We can find the tension now using either equation 1 or equation 2. They're still going to give us the same value. So in this case, I've picked equation 1. We have equation 1 giving T equals M multiplied by G minus A. Okay, remember equation 1? You can go back to the top and check. So if we work this out, then we're going to find tension as 0.82 newtons. Okay, find the tension as 0.82 newtons. Okay, so we have solved question 2. We have found the moment of inertia, and we have also found the tension in the cord. Okay, so we move on to question 3. Question 3, you can read on. Okay, so question 3 here, we have a wheel of that radius and the radius of duration given. So it's rolling down a slope as shown in this diagram here. So we want to find the linear speed when it reaches the bottom. Okay, because the height here is simply 0.4 meters or 40 centimeters. So we want to find the linear speed of this wheel when it reaches the bottom of the slope. Okay, and we also want to find how fast it's rotating in revolutions per second at that time. Okay, so the linear speed it's moving with when it's at the bottom, and also the angular speed at that time. Okay, so here is our wheel. Here is our wheel. Okay, so it's rolling down the slope. So for this one, we have to consider the conservation of energy. Okay, so we know that the potential, or rather the total energy at the top must equal the total energy at the bottom. So total energy here gives us potential as well as kinetic. So notice that for kinetic, because this is a rolling object, we are going to have both translational kinetic energy as well as rotational kinetic energy. Okay, so we have potential energy plus the total kinetic, meaning translational as well as rotational, at the top of this slope must equal the total at the bottom. Okay,